way back in the second week of the class. So we said this, say x was a binomial NP. Right? So by the random variable, what it will mean? We meant probability x equal to k was given by n choose k, p power k, and 1 minus p to the power n minus k. And k was between 0, 1 up to n. And we sort of motivate this idea by this random variable by thinking of it as n coin tosses, where each x was a head or a tail at probability p. They were all independent, and x was the number of successes in n tosses. And then we also showed an important theorem that if p gets smaller as n gets larger, that is, p is very small compared to n, so p is like lambda by n, then we showed that the limit as n goes to infinity, probability x equal to k was e to the minus lambda power k by k factorial. And this we saw was a legitimate distribution by itself. We called this as Poisson lambda. And we said that Poisson lambda was the distribution that y equal to k is e to the minus lambda power k by k factorial for k in natural numbers remain 0. So this is where we were at. Maybe the third or fourth week of the class, we had shown these two results. And this I had called as the Poisson approximation. Right? And I had motivated this idea by saying that typically this is hard to calculate. So for large n, and let's say you take k to the order, let's say square root of n, for example. This is hard to calculate. Computationally, it was hard to calculate because you have all these factorials. So that's why one of the reasons I motivated the fact that you need an approximation. The approximation was valid when p was small compared to n, and p was lambda by n. So today I want to do a different approximation. I want to do so let me pose the question. So the question today I want to understand is the following. So what if I fix a p? So I fix a p which is not at the boundary. That's it. So p is kind of close to a half. Think of it as p is close to a half, and it's fixed. And what is the behavior of x? So what is the behavior of x as n gets larger? So let me proceed to answer this question. So let me just rewrite notation a little bit. So let's just rewrite notation. So let me just call x, since x was equal to summation I equal to 1 to n xi, when each xi was Bernoulli p. Let us denote x as s sub n, which is just the summation I equal to 1 to n. So s is the sum of n Bernoulli. Very good. So now I want to understand the behavior of Sn as n goes to infinity. So what's the behavior as n goes to infinity? So the Poisson approximation case, I took probability x equal to k, right, for a fixed k. That's why I approximated. So here, let me do the following. Let me just try and see this. So let's take a and b real numbers, a less than b. Okay? And I want to understand the chance that a is less than Sn is less than b, right, is what. And again, the behavior as n goes to infinity, and also as n goes to. So suppose I want to understand this. So now let's do some formal calculation. So now the key thing is that, of course, this will change with n, right? And that will definitely happen. But let's just check broad, let's say, signatures. Let's check broad signatures. So what are the broad signatures? So the first thing you know is that we've already done this before, that the mean of the random variable Sn is equal to n times that we have seen. Binomial has mean n. We also know the variance of binomial, you can do it many ways, is the variance of the sum of I equal to 1 to n of the xi's. They're all independent, right? They're all independent. So the variance of the sum is the sum of the variance, right? And we know that each of the Bernoullis have variance p times 1 minus p. There are n of them, so variance of Sn is n times 1. So if you go back to this idea that formally the range of Sn, right, you would think it as what's the range of Sn? You would think it as start at the mean, that is n times p is the mean, right? And then you would go minus the variance, which is standard deviation, which is square root of np times 1 minus p. On this side, you'd go np plus square root of np times 1 minus p. So that would be formally the range of Sn. That's how the spread of Sn is going. So Sn is going to be centered at the blue, so it's clear. So Sn is going to be centered at np, right? And formally speaking, you sort of range across the standard deviation. This is like the standard deviation. So that's what you think Sn is going to be around. So A and B, if you want this probability to be large, A and B better be of this order. So if A is of the order of the left hand side of the interval and B is the right hand side, then you would have probability, large probability. What we think. So now let's try and see this other idea. So Sn is always going to be around np. So if A and B are fixed numbers, your Sn is going to cross them in some sense. So you have to go and choose if you want to find a meaningful answer to this question, you have to keep moving your A's and B's with respect to n, because Sn is going to keep moving around np as it keeps going. So here's a simple a next question. Let's say a modified question. So that's our gut feel that Sn is going to be centered around np and rotating around and revolving around the square root. So what you do is you take an A and B in R, A less than B. You look at, instead of looking at the chance that Sn is between A and B, you look at the chance that Sn is between, let's say, it's going to center at NP, so it's going to be, let's say it's NP on this side, Sn, on this side you have NP again, but then you sort of add and subtract according to A and B. So let's say a times square root of np times 1 minus p plus this, plus on this side you have b times square root of np. So you try to understand how this probability will be. Rather than just look at a fixed a and b. So that will just be so meaningless. So but that's equivalent to saying, let's say I rewrite this a little bit as a is less than equal to Sn minus n times p divided by square root of p n p1 minus p is less than b. Less than equal to. So this is something I can understand. So I've standardized my random variable Sn around its mean and I divide by square root of it. So let me quickly recap what I'm trying to understand. So earlier we had to do this Poisson approximation when p was smaller, was lambda by n, and I said that as n goes to infinity, we had this thing called the Poisson approximation. Now what I want to do is I say that let's say p is fixed between 0 and half, and say p is kind of close to half, for example. And how do I understand the behavior of the binomial as n goes to infinity? So one simple observation is that the mean of the binomial is n times p, and the variance of the binomial is n times p times 1 minus p. So your range is going to be around np with plus or minus square root of np times 1 minus p. So one thing one could understand is that a correct question to understand is that how large is Sn away from np and standardized by the variance. So I take Sn minus np divided by square root of n times p minus p and look at between a and b. How does this probability behave? So let's try and answer this question. So with that. So now here's an answer. Let's try and do the answer. So I won't give all the details in the answer. I'll give you the broad scheme of things. So what is this probability? So this probability is what the chance that A is between Sn is between np plus square root of p times 1 minus p and np plus square root of b times square root of np. That's what it's like. So this, if you think a little bit, is just the same as read at the binomial probability, same as k is in some set an, probability of Sn equal to k. And that's what this is about. What is an? Where an, what is an going to be? Where an is equal to the set of all k such that np plus a times square root of np times 1 minus p is less than equal to k is less than equal to np times plus b times square root of np times 1 minus p. There's no sort of ambiguity. K is in let's say natural numbers, even 0. now, maybe I can just move this across. So I just have to do that. Very nice. So now, that's my Sn. So what's my Sn going to be now? We know Sn is same as summation k equal to a and an. Let me read this in blue, so that's sort of a little different. So now k is a, and what's Sn equal to k? That we know is n choose k, p power k, and 1 minus p to the power n minus k. Right? That we know. So this we know from before, right? So this, let me call this in green, so that is something different. Very nice. So now, once I have this, now I can expand, right? So now, this is same as the sum from n equal to k, k equal to k and n, and this is just n factorial, right? By k factorial, n minus k factorial, right? And I have p power k, 1 minus p to the power n minus k, right? So now, this is where I'll do a big jump. There's something called Stirling's formula for approximating factorials. I don't know if you have seen this Stirling's formula. So it just says that n factorial is of the order n power n e to the minus n square root of n and so on and so forth. There's a formula like this, Stirling's formula. And there's another one that you need to know. This you learn in analysis too. This is called Riemann integration. So this just says that the sum from, let's say, 1 over n k equal to, let's say, sum, let's say, 0 to n for the time being, f of k by n will converge to, let's say, integral 0 to 1 f of x dx. So an idea like this has to be implemented about. So this, what one could do is, one could use this to show that as n goes to infinity, the above sum converges to. This is a big jump, which I don't want to explain properly because it will take a long computation. This big jump will converge to integral a to b e to the minus x squared by 2 over square root of 2 pi dx. So that's a sort of a big jump I'm making, that this sum will converge to this integral. So that's something that I will not, it's not part of this course in some sense. I cannot show it because you need to know how to do this approximation. And this is also a very sort of a well-used idea. It's non-trivial in that sense. So to do this. So what you get is that the probability that Sn, Sn is interval converges to a to b e to the minus x squared by. Green and hear me? Can someone just confirm that? Thanks. So now, what have I shown? I've not shown. I've told you two aspects of it. One is that the probability that Sn minus Np divided by square root of n times p times 1 minus t between a and b was the correct thing to look at it. And look at the limit that then goes to infinity, it converges to this integral of a to b e to the minus x squared by square root. This has two aspects to it. One is Stirling's formula, and the other is this analysis 2 material of how an integral is formed by Riemann sums. So these two ideas will give you this idea. So give you this result. And So this is one way of understanding the probabilities of Sn. If Sn is centered around n times p, and how does it behave around that np? It's in a range of square root of n times p times 1 minus p, and one can understand how these probabilities are via this integral that we have. For large n, that's how it looks like. So this is called the correct the discovery was made by Demoivre early on, and this is called the Demoivre-Laplace central limit theorem. This result is called. It's actually a much more universal phenomenon, but I have sort of established for you in the binomial case, modulo these two jumps that I've done with Stirling's formula and this Riemann integration. I will provide you an article on the weekly emails where you can read this proof properly. It's nicely done. And it's understandable at your level, provided you sort of know this Riemann integration and then Stirling's formula. Very good. So then, what's happening to this guy in the integral? What is going on? So now, there's something I want to discuss now. So what the integral is doing. So, like, what has happened to the integral? So now, so that's what's called the normal random variable. So let's do a little bit of a sketch before coming to normal random variable. But let's just do it's called normal. So before I define the normal random variable, let's just discuss this density function. Or maybe on second thought, let me define the normal random variable and come back. So x is said to follow normal random variables with mean 0 and variance 1. Because I have not told you how mean is 0 and how variance is 1. Let me come to a second. If let me call this z, because what I call it z. If z has PDF given by f of z is e to the minus z squared by 2 over square root 2 for z. So that's what a normal random variable is with parameters 0 and 1. Of course, there are several questions that remain. So clearly, that is f a density. Is f a density? So some properties are obviously clear. F is non-negative. Z squared is continuous. E is continuous. So f is continuous. That's part of easy to see. To show that the integral is 1 will take some work. Okay, it will not be easy to show. So that I will not do this as part of this class. Integral fx dx is equal to 1 will take some work. I'll just say we'll assume. You might learn it in complex analysis or analysis 3 as you go. How to do this. So that you'll assume that the density function integrates to 1. So now let me try and understand how this random variable is behaving. So let's try and graph the density a little bit. So let's try and graph it. So here's the axis. Here's 0. So I don't know if you've done enough curve sketching in class 12 or otherwise. So this particular function is e to the minus z squared by 2. So as z goes to infinity and minus infinity, this function is going to go to 0. Right? So at 0, it's the highest. It's 1 over square root 2 pi. Right? 1 over square root 2 pi. That's the highest at 0. And other than 0, it sort of decays. So first it is concave down up to some point. And you can find this point at which it turns direction, and then it comes down, decays like this. That's how the function will look like. So we get it properly. So yeah, it is this. So it will come down like this, and then change direction, and then come down like this, and change direction. That's how the function will look like. So, and some observations you can make is the function is symmetric around 0. Right? Symmetric around 0. The function decays to 0 very fast as z goes to infinity. So as z goes to plus or minus infinity, f of z goes to 0 very, very fast. So, and f of 0 is the maximum. Right? So 0 is the max. That's an argument. The argument with the maximum. So that's one thing. That's one observation. The next observation is that there is no antiderivative. So there is no antiderivative of f. In the sense that so therefore integral a to b f of z dz, which is integral a to b e to the minus z squared by 2 over square root 2 pi dz, this has to be calculated numerically. You cannot do it by your standard 12th class mathematics. So e to the minus z squared by 2 over square root 2 pi dz can't be evaluated the standard way. There is no precise value of the antiderivative. There is no precise expression. But the integral exists. What will happen is that there are numerical tables by which you can understand. So there are numerical tables called normal tables that provide evaluations. So that's one of the second observation. First observation is the graph, that the graph is simple. The zero observation is the density function, we'll assume. We will not bother about it, why it's so to calculate probabilities, you'll have to go to the normal tables. You cannot do it without by hand or by guessing the antiderivative. It's not possible. There's not even a close approximate antiderivative. You have to do numerical. But then, how do you find out probabilities with regard to z? So that's the next question I'd like to understand. So here's the question number 2, or question number 3 in some sense. How do you compute? How does one compute probabilities associated with z? So here so you can't keep on if you're doing numerical tables. You can't write a table for every A and B. You have to have some system for which you write, you tabulate these values, right? These values. is for A and B. So let's observe some properties of the integral. So let me copy this picture so I can see if I can copy it properly. Very nice. Come on. Let's see. Let me do this. Don't copy the whole thing. Very good. Let's copy this. Very nice. Very good. So let me go and erase all this. So what am I interested in? I'm interested in interested in what? Probability. If you look at the motivational question that I came up with, I came to this by the binomial approximation. So I'm always interested in probability A less than x, z less than equal to b, which is integral a to b, e to the minus z squared by 2, minus z squared by 2 over square root 2 pi dz. That's what. So I make this as yeah, that's okay. This is what I want. So now what is this? Let's say A is here, and let's say B is here. This integral, if you know by either 12th class or otherwise, integral is just of a non-negative function is just the area under the curve. So this is the area. This region, and by analysis 2, you learn that these both these quantities are the same. So the probability that A less than Z less than B, which is equal to this integral, is going to be given by the area under this curve. So that's something that we understand very well. So now we can use the property of the function to see from what all geometry can I do to get this area. Here's the first observation. So let's say observation 4 or answer 4. Let's say, let me call this answer 4. Answer 3. Question 3 is this. Let's say answer 3. So now the first thing you observe is that let me go and copy again. Let me see the picture again. See it comes awareness. Cool. Let me erase all this. Okay, let me erase all this. Right. So the first thing you observe is that let me call this point as A here or alpha here, and let me call this point as or minus alpha here, and let's call this point the symmetric point across here as alpha. Okay. So I have not drawn it correctly. The distance is the same. Then this, let's say, green area under the curve, because the function is symmetric, is going to be the same as this green area under this curve. These two areas are the same. So these two have the same area, right? So same area. I won't show it can also show it explicitly. So all I'm saying is that the integral from minus infinity to minus alpha of e to the minus z squared by 2, e to the minus z squared by 2 over square root 2 pi, because the function is symmetric, is the same as on this side. I go from, let me just mark this in a little different color, so you can see it. Make it in blue. The blue region on this side is same as this region is what? Alpha to infinity. Alpha to infinity of e to the minus z squared by 2 over square root 2 pi. is moved a little bit down, so that's clear. Right. So this, you can also make it rigorous using your 12th class mathematics. You can just take it as, you can do a substitution, let's say alpha to infinity. You could do a substitution, let's say u equal to minus z, substitution to get this. And this you'll learn as 2 again. I won't making it bigger. So that's one observation here. So the area on the left hand side is the same as area on the right hand. It's quite cool. So it's observation 1. Then the other observation you can do is that once you have this observation, so you also have one more observation, because you know it's a density function, right? Let me make so density function. So what is the green? The green is probability of z less than equal to minus alpha, right? That's what the green is. That is minus infinity to minus alpha e to the minus z squared by 2, sorry, z squared by 2 over square root 2 pi dz. And that's the green. Right? Now this person on the right hand side, what is that? So let's go right hand side. What is that? That's just, I start off with my alpha to infinity e to the minus z squared by 2 over square root of 2 pi dz. That's what I have here. Very good. That's what I have here. But what is this person? This person, because it's a density function, this is the same as 1, the whole integral is 1. So I'll write it as the whole integral is 1. I'll write it as minus infinity to infinity e to the minus z squared by 2 over square root 2 pi dz minus infinity to alpha e to the minus z squared by 2 over square root 2 pi dz. Right? That's just a property of integration, right? This is the whole integral minus this guy is going to be this guy. This is a jugglery so far, right? I'm just doing a simple jugglery. Ready this. But the density function, so this guy is 1. So it's going to be equal to 1 minus the probability from minus infinity to alpha e to the minus z squared by 2 e to the minus z squared by 2 over square root 2 pi dz. Now let me flip it a little bit. Let me move this across to this side. So I start off with the green. The green is this. So how do I come to this guy? This I know is the same as 1 minus the probability. So maybe I should not do this. It's okay. It's fine. This is the first person I have. That is this equation I have for the green guy. For the blue guy, I have this, this, and this. And what is this? This person here is just 1 minus the probability that z is less than equal to alpha. So you have an interesting relationship. The probability z less than equal to minus alpha is 1 minus this, which we know is also the same as probability of z bigger than alpha. So what have we shown? So we have shown that these two are equal. So we have shown an interesting fact by this area computation that the probability of z less than equal to minus alpha is same as 1 minus the probability of z less than equal to alpha. So the minus alpha and alpha have this relationship. So this is the green area and this is the blue area. The green area, and this is the blue area. So unique property because of the property of the density function. Very good. So I'm almost there now. Let me count. Now I'm almost there. So I have this property now. So what was I interested in? I was interested in calculating the chance that, so probability that A less than equal to Z is less than equal to Z. So that's just, as we write like this, minus infinity to A e to the minus Z squared by 2 over root 2 pi dz plus minus infinity, or let's say that around, minus B. First write A to B. Okay. Is A to B, and that's the same as minus infinity to A e to the minus Z squared by 2 over square root of pi dz, or minus B is B Lazare and minus infinity to A e to the minus Z squared by 2 over root 2 pi dz. So as long as I know how to compute these objects, right, if I have a table for these objects, that's good enough, right? So you need a table required for these objects. But then what I do is I'm claiming the following. Here's a claim that I'll establish quickly, and I'll take a little break after that. Here's a claim. I'll state the claim and I'll take a break and come back and show it. It is enough to have a table of numerical values of integral 0 to A e to the minus x squared by 2 or z squared by 2 over square root 2 pi dz, or let's say 0 to alpha, let's say 0 to alpha, or let's 0 to alpha for alpha positive, to compute probability of A less than Z less than B for any A, B. That's the claim. So let me make this claim in the room. So that color combination is standardized. Oh, come on. Change the color. Okay, I'll do the proof when I come back. So all I'll do that I'll show you that I can, for any A and B and R, if I want to compute this probability, it's enough to calculate from these sort of ideas. So maybe I'll leave you with this document, the recap of everything we've done so far. So you can think about how to do this claim. I'll take a 5-minute break and we'll come back and do this. So claim is that if I know only this numbers from 0 to alpha, then I can do this for any A and B using this idea and this idea.